Okay, good morning, it's Konya, and I started playing the Ultimate Nerd Game, or TUNG for short, which led me to the same issue which I had in Minecraft already, and that is adders. I made a Ripple Carry adder, and I'm not gonna go on details about that. Ripple Carry adders are big bad for obvious reason. Every player, especially Minecraft players, should know that. That's because carry ripples, whatever. So, in this game, there is no relay or piston. Normally, I like to have these because they allow the usage of an instant carry adder. Yes, so the problem is I cannot use an instant carry adder. So, what are the first type of adders which come in my mind? And like if I go in Minecraft and like there's some weird abstract type which doesn't matter for now. Go back here. There it goes. That is a carry look everywhere adder, and that is like the first adder which I would choose right after ICA. Probably I never done that because I always have been using ICA adders, instant carry adder. Here's another interesting type of adder which has like some logic at the beginning, then some wire which just passes through, and one which just goes the upper way. So we got at the end an XOR row again, and at the beginning something like an XOR. It's actually XOR, and in the middle we have like a bunch of whatever stuffs which do carry optimization. However, because I did not want to make that logic madness, I said I'm gonna use the CLE. There are people which have built CLE already in this game, and thus I thought it might be nice to know that. But I'm not the kind of guy who just goes and copies stuff, so I want to understand how does CLE work. For that, I watched Mr. IO's video to see how it's built, to extract the rules of what has to be done. And as you can see, you got this triangular shape here, and that is basically because we're testing a bunch of combinations. That is, for each digit in the number, we test all previous digits, and with rising, like you can see, each of these rows is one more, and that's because we go one bit up, so we have one more bit to check. And that's how this triangular shape gets created, and that's the same in the Ultimate Nerd Game. You have like you also have like this triangular shape, but it looks a bit different. The advantage in Minecraft is that you just passes the value like directly through. It's diagonal, but that doesn't really matter. So I've been writing a big ass document like last night, where I tried to sum up my knowledge of how and why ICA works and how that is related with CLE. And I was like, okay, in ICA you have like this bridge here which can be opened or closed with relays in the carry line. And if we don't have this object which can open a wire, like as in so that the throughput of the wire is instantly without delay, a single transistor or gate would already delay the signal, which is what we want to prevent at any cost. So we need something like a relay or a piston or whatever there is to instantly cut and open a wire. Like, the effect of opening and closing doesn't have to be instantly, but the actual throughput, once one of the two states has been reached, needs to be instant. Like, if it's closed, it needs to be instant travel there, else it won't optimize it. That's why I consider ICA one of the most superior adders in terms of carry optimization speed, because, well, it's instant because using the relays you don't have any delay. Any other kind of adder optimization, from my knowledge, has some form of logics which always implies gates or transistors, and that means it's always slower, which ICA doesn't have. So the next version of TUNG, which is Logic World, gonna have relays due to people loving ICA, I guess. And yeah, so I've been starting to write this section about CLE, and I was like, yeah, okay, if we don't have this, we need to find the conditions for CLE, and that is, if we have the input, the carry input here, we need to calculate what the possible inputs are. So for example, the first output bit just has the carry in, and the second has the carry in and this normal output of the first half adder, and then also the carry output of the unit before. So like these are from the first bit, and we want to calculate this input here of the second bit, and that there's some neat little way how I formulate that without using these weird generate and propagate words, because they are not really understandable for me. And that is, I like to use the word consume. So a carry gets consumed in this unit when this bridge is open, because then it's no longer passed through, it gets consumed in this digit. So whenever this S output here is 0, is it 0? Yes, whenever it's 0, the carry will go into this half adder and then be outputted into the final output. It will not be carried over, because it can't be carried over, because here is a 0. So that's, well, you know how binary addition works, just refer to that, test it out for yourself. If this is 0, then the carry will always be consumed. There's only one relevant case of 4, but it doesn't really matter. That's why we need this S to be set, or to be not set. Wait, it has to be off so that the carry can pass. So basically this needs to be inverted at all points. Let's not care that for now. We get this triangular shape here because we have the pass through values and the carry in and all the other generated carries, which however also have to like pass through the gates, I say, so they must not be consumed. And that's how you get this triangular shape with all these combinations, and that is basically what the Minecraft CLE does. It has exactly this kind of how should I say, term, like this term and this term to determine the carry. Like if I look at this, we got, like, this is the Xor Gate. The Xor Gate refers to all these kind of OR symbols here, and the AND gates are the torches over here, like which is always like this one that will be S2, I guess, or S1, and this is the next S, this is the next S in my terminal, in my formula. And then we got yeah, that is how this somehow works. So basically you got all the S values like here in this row, and they enter these things, and I don't 100%ly understand this yet, and I have to. However, that is not my main issue right now. I kind of get that this combinational logic is kind of relevant, and that it looks everywhere, and everywhere is defined in my document like here. So the point is, I always learned that propagate is generated, or is created by ORing the two inputs. At least that's how it is in Minecraft, and that's how it is done in this adder. You just OR these, yeah, right, no input permission, awesome. It doesn't matter for now. Anyway, this wire is only on the propagate, this weird term is only on if either of these or both, but it doesn't really matter. So any combination of input is that, and luckily I found something on Wikipedia, which, yeah, awesome source of knowledge. Nice, my Chrome is stuck again. Cool, I'm just gonna restart it. Here I also have the CLE thing from Mist.io, and he also wasn't clear about if it has to be Xor, or like he just showed how to build it, not how it actually works and why it works, while the case why is more not that important. Anyway, I stumbled across something, and that is that CLA uses the same kind of terms, and I was like, yeah, I recognize these, but isn't CLA some kind of different form of it's not equivalent to CLA, and apparently from what I see here it's the same as CLE, except that it kind of puts brackets or like parentheses around parts which are the same. No, can you not call me? Oh, okay. Anyway, so we see this structure of these terms like everywhere. No matter what you try to optimize, you always get this triangle. And yeah, here it is. So if you're in the Wikipedia article for implementation details, you can find the section of generate is generated by ANDing these two, while the propagate can be generated by either of the following statements, and that is XOR and OR. And that is kind of, I never heard this before, it's totally new to me, and I was like, that would explain why some people use XOR and some OR and nobody cares. Except that OR is faster than XOR for obvious reasons. So it would be convenient to use OR, and I was like, I need to understand why is OR equivalent to XOR. That is like the main question which I have right now, because the rest is like, okay, I can totally tell where these things come from. There's like a bunch of there's like, this is like the cause of the total mass confusion. Like, you have this CLA, and it's like, no, that is not a CLA, that is this type of edit, that is that type of edit. That, in general, CLA is, from what I understand it, this concept of optimization to carry, and there are like plenty ways of Cookstone, and there was another one, I don't know where it was, Brent Kung editor. That's names one heard before, and then there's CLE, which obviously has no Wikipedia article because it's a Minecraft thing, but it's basically just CLA with all these terms bummed in huge logic grid. And okay, whatever. For me, the point is now understand why XOR is equivalent to this recording right now, why it's equivalent to each other. And for that I made I made this small test site. Here we got the first half adder of the adder, and this is the XOR at the output. If you know ICA by hand, you know that there is in the second half adder no more AND gate, as in you don't generate a carry there anymore, because that is done with the pass-through. That is basically what I described in this huge long document, which is not really of importance right now. However, that means we need to get the carry of some form in a different manner. And for that, let's have a look at this case. I have a bunch of them here, like 5 bits, but if we only look at the first one, we already get an issue, and that is, if we have one single bit. Why is this red? This should be yellow. Oh damn. So yellow in this case means it's just one bit which is on. Then we have that output bit, the first one, on, obviously, no big deal with that. And if we go like this, then that second lamp should be on. So that is the first trivial case. That is, if the carry here is on, then the carry has to be on over there, and that is the output 01 in my document, like the first part of the term. But we also have the case where we could generate that same result if we have carry in and the first bit set. So that is the second part, and this one doesn't have an AND output anymore for non-ripple reasons. So we're a bit stuck here and say like, okay, what do I have to do now? And that's what I basically already wrote down, and that is we have to check that this one here is off. How to actually check that? Well, that is quite simple. For that, we just let's get rid of this for now. We go here, create one of these inverters, dump one of these. You know, that's actually a bit of an issue. I need to put that type of block there, and yeah, I'm still new to this game. I started yesterday actually. I mean, I can use it, but it's kind of something. So there we go, and then we got the first one set. So this one needs to be on actually. So I have, or let's say I should invert this. So I'm just gonna put inverter there, because this is like real nasty. Or actually, let's just use this signal here. It's like the same. Let's put it like this and get rid of that one. So this would be the inverted signal. This gets messy, I can tell, and this will probably be even more horrible in future. We do the same with the carry out. We want the carry out to be present at this point, and it has to be on. So this is a simple AND gate here with one inversion here and some there. Actually, I can put this here too instead of that one, because then I already have the diode there, or the whatever repeater, whatever you may refer to this, and then we have the output going. So this should now be off for obvious reasons, because the carry is off, and if this is off, then it also should be off. So it's like, this is like the type of thing which is relevant at this point. However, I removed the case that this one here directly gets power to that line, which is kind of an issue. So let's put that back here, and that is what we can do by simply putting like this fellow here and connecting that to, I guess, this output. So if there is a generated, yeah, I'm using generated carry, or a carry in the first unit, we obviously want to have this lamp, the second bit, on. But also, if this unit is not consuming the carry bit, which is the carry in this case, then we also want this lamp to be on. That is the case if we just have one of these on and the carry on, and then it should also be on. So that is this one and this one. That's the two cases which I described in my document, which is scrolled horribly, which is this one, carry in and the first non-consuming bit, and the generated carry of the first bit. So here we got the carry 0 with the carry 1, and that gives the carry 2 or something. So knowing this, I can actually continue to add another bit. So this becomes real nasty at some point, because I'm building this in some way. So let's do it like this, and this is an XOR, so I can practically just connect this to there, and it still works. But now I said we want to add a bit, so let's add the trivial case of this one outputting here. But I'm gonna change this a bit. Well, I'm just gonna put a pack here and connect this. So this is the same as before. It's off because it has to be off. So if I turn this off again, we can see the classic ripple effect with well, because this is not synchronized, it currently just is a mess, but it should not ripple. It is not rippling because it directly checks both cases of a carry being generated here instead of rippling it through this unit. So the next case, or let's not go to next case. At least I'm gonna, well, I edit the next unit, so I should actually like have that thing placed. The at least this carry should be working. So how to do that? I'm just gonna put a pack here and then connect that to there, and then we're gonna find all cases of when the carry will be generated. The first one and most obvious is obviously the carry of the unit before, like so. That is if these two are on, then that one is on. It doesn't really give a poop on colors, okay. So there we go. And so the next step would be, let me see, to put the other conditions, and that is this output here is on in combination to it's getting not consumed by this unit here, and that can be done. Did I connect this? I connected it like this. I'm gonna put it a bit differently here. This is a bit of a mess. I'm just gonna go and put like a diode like here, so I can simply grab the signal from there without any pain. I need one inverter for the condition, and that goes to there, so that is the pass-through signal. So that means that this unit is not consuming it. And now we need the generate from here, which is also not really passed through a diode, which is a bit of a pain. So I'm gonna put something like this here too. Whoopsie doopsie. Like so. Now I can just simply connect this to here without any form of weird connection thing. So, and this needs to be here too. So that is the case if we have one on here. That means that this enables, and I should maybe connect this. And the case that this one generates, no, it doesn't generate. I failed. I need to grab the, what is that, the normal output that needs to be inverted, so I grabbed it from there, and instead I used the wrong one here, so it has to be the inverted one, so something like this. You see, this is quite confusing. But I will name this video, and I think I'm gonna upload it for fun. I'm gonna name it me trying to understand CLE. And I'm gonna open that document I made on my other monitor. Just gonna move it over so that I am actually able to have a look at it and don't get messed up. So what I need here, I need the propagate. Now I'm talking like that. I need the normal output of the first half adder to be sent to each of these units, always. That is something, you know what? I have an idea that is cleaning up, else this will be a mess. I need the normal output of the of each unit always. So that is something. This is actually the normal output. So this normal output straight goes over there. Bam. Same with this one. This normal output straight goes over there. That's just, it is like that. But that also means I need that other output, like not the other one, but at least the inverted one of that, which is that one. So if this one is on, it consumes the carry, because then this one is off. So if this one is off, it consumes the carry, and because we are building AND gates to make all the combinations working, this one needs to be on. So for the combination terms, I'm going to use this output. And then we got the generate, or the carry output of each unit, which however has to be inverted if I am right. And that is, I should actually do the same thing here. No, I just leave this wire as is. It's quite outside, so it's not really much of an issue. So this one needs to be inverted too. It currently is not, which is an issue. So I could just connect it to here, and then it's inverted, and hope that it will work like this. I think I need to do the same here, like this. The advantage of these things is, for the people which come from Minecraft, is that they are basically diodes, and the effect is that if I connect multiple wires to each of these knobs, these wires will not intersect with each other. Like, one can see it like properly here, I guess. It's not going back to there and then flow over to there, so it's not going. This is a plain output, and it's one-to-many output and not all merged output. So back to the start again. So for simplicity, I'm gonna put another one here, another pack, and the inverter of that one goes there. So currently the carry is enabled, so this is off, so all combinations of that will work. So this is the point. Now I can span wires easily. So this is the point where I need to just set up all the combinations. We start again with the first kind of carry, which I simply have like this. So I'll connect these wires, there. And we said we had two conditions for here. In this one it was just one, that's the carry in this case we have two. So what are these conditions? The first condition is the carry out of, wait, that's the second bit, so the carry out of the first one, the first unit, which is currently not the case, and I messed this up again, because I don't need the inverted one. I need the non-inverted one. This is super confusing. So I'm just gonna put it like this. And I need that other case, and that is when the carry. So basically, let's kill this one. So I need to turn all these off for simplicity. So we have the case that both of these are on. So that is this wire, we get a carry here, and that is for sure. Currently, I'm gonna turn this off for simplicity, so that is 2. If we have 1 plus 1, that's 2, certainly true. So what is the next condition? The next condition obviously is if the carry in is on, and this one has just a simple output. So that is what happens here. We use the simple output from there and the carry from here. So that will be the other condition of generating that output. I think I'm gonna realign this like real quick, like soon. And as you can see, it's properly working because this line is preventing the carry to happen from here. And even if we have a carry, but we consume it like here by just not outputting something, then this other line tells it, hey, stop it at this point. We're not gonna like continue here at this point. So let me fix this layout. I'm gonna put this here and this here, and then it should look kind of neat compared to before. There we go. So that's how it looks now. Did I mess this up? No, that's how it should look like. So what is the next step in this? We have alright, it was this carry. So if we have well, this is all off, and so this one goes off too. What is the next, or like the carry condition for, so this one? As you can see, the bottom two units work perfectly already. Due to how this optimization works, refer to my document to understand that. And here in this case we have the case that we have 3 plus 1, which is 4. So we need this one to be on. And how do we do that? In this case, the carry is the significant position. I'm gonna put it like this to see if that works. It won't this wire to be on, and that is because we are checking for the carry, and we are checking for this consumer, and we're checking for the consumer over here. So if the first bit and the second bit don't consume, that's what these two wires are for, don't consume the carry, and the carry is on, then we got an output here. So this output goes off if either the carry is off, if either that one consumes it, the first one consumes it, or the second one consumes it. Okay, cool, so that is the carry. So next thing we care about is the carry generated in this one, in the second unit. So we can do that, or test that by putting this next AND condition here, so that we have that one, that is a wire for the AND output of the first half adder, and I need to put it back here, connect this to there. So in this case, there we go, we got a carry, but this is not properly set up yet. We don't need to consume it, that's important. So okay, in this case we have either carry gets generated here or not. So this is not, this is it gets generated, and this one says it's not consuming it. So if we are consuming it like this, we see it's gone, like the carry is off. That works like perfectly. And then there is just one last condition of how to generate that. What was it? Carry, right? And that is if the second half adder actually has both levers on, both inputs, so we get an AND gate here, an AND output. And I'm gonna put that one right next to it again for the simplicity, for the accessibility reason. So this is the AND output. You can see the lamp is red, for that's what it stands for, and another pack here. I don't know why it's pack and not something else. Well, and then it's connected, and there we go. So that will be the last of the 3 conditions. So I think one can see the pattern at this point already. I could go here and like do like make this a bit more generic by doing by also inverting this simple carry and putting it there, and then we got that known triangle at this point, because here's the actually I can like put this here and that there and connect this to then have a direct connection to here instead, if this wouldn't be there. So then it pretty much looks like this, which is like a perfect triangle shape. Certainly perfect. I mean, look at this geometry. So I could continue this further, but that's not the point of it. The point of this is that I want to know what the difference between XOR and OR is. This is currently working with XOR, and I figured out for myself that if you use XOR, it's the difference between we consume or we don't consume the bypassing carry, and that is the main difference which we check with the normal outputs, the XOR outputs. If we, however, change this system to work with OR, oh wait, that's this lever. Now it's using OR. So if I output both levers, we get an AND output and an OR output, or let's say it like this. And as you can see, it's not working. So why is it that CLE works, that Wikipedia states these two are like the same, and I don't know. This is kind of a bit hard to understand now, because that is where the actual pain starts. Why is it working that way? That there got to be some kind of difference, some kind of way how it works, which is kind of confusing. If people know, oh, shame on me. People I know, which if they know that, whatever. So because currently we have a carry out here, which happily jumps there, which is totally fine, because that is what's supposed to happen. But we got that unit on, which should not be the case, because that is OR and not AND. So what could we do at this point? We could, well, AND this again, like this wire with that wire. We could like make an AND gate here. If this is on, we don't want that one to be on. That is kind of stupid. I don't know. So for that, I think I'm gonna check this CLE design. I'm quickly gonna grab it over. Cell B. Okay. Oh, I hate people which like don't fit their builds in a box so that it doesn't intercept with anything. Oh gosh, that lag. Well, okay, it's connected to this build, so it's obviously huge. So there we go. Copy. I think I should maybe. Why is that actually twice here? I don't get it. So I'm gonna make this a little bit small so that it won't eat that much CPU. It's on 11 FPS. Are you kidding me? I said shrinking, not. Got it? Okay, whatever. So I copied this, so I'm gonna go back to my plot and paste that. How long am I talking nonsense already? Wow, almost 40 minutes, gosh. No. No. So there we go, there it is. So I don't need this part here. OMG. In like the Ultimate Nerd game, it's I don't know, I'm probably gonna prefer that as logic game over this. Well, obviously I'm gonna, because it's just so much more handy to control it, although it's crappy as of now, in a way. I mean, you have no click distance, and I can just delete stuff, like with one single letter instead of with a mouse click. Well, no matter of how this works right now. So this currently, this is the inverted output here in this, which basically is the same as one of the blockers in the game. Like, these pipes are set it down, and these slabs basically are nothing else than powering each of these ant blocks I placed down, the triangle ant blocks, that's these torches. Like, so there we go. We got like these wires here are actually, oh gosh, that lag is horrible. Like, these wires go everywhere. That's the same as the slab, as what the slabs do, except that these at some point merge with the one of the others. It's like, I guess that is the same as when, oh gosh, my computer can't handle this anymore. Wait. I can fix that, probably. If it's not fully dying to that point. Let's not have so much chunks to render and not have so many FPS. I'm fine with 30 things. So, and if you may reload that. I don't know if it helps. Oh, it's still laggy, whatever. That's the problem if you have like more than full HD and such an old computer. So back to this, and I hope this works by now. Oh gosh, I fear my RAM is just full. I bet it is. So each of these blocks here is one of the torches in that triangle, and I'm not quite sure. I think I need to understand how this is actually set up, because just give me this and don't do anything funky again. OMG, no, I don't want to zoom in. Okay, this is getting horrible. Like, real horrible. Okay, there we go. Oh, now it's fluent again. I don't know which of the games is actually blocking all of the graphic. I guess TUNG, but I'm not sure. At least 2 3D games or 2 graphic card games is real pain in the butt. So we got all these, well, here it's propagates, let's say, or these OR outputs of the inputs, and they go to each of these torches. Like, this is just like not really merged. This is like a bunch of wires going from here to there, 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 and same goes for that one, from here to there, from here to there, from here to there. So don't mind the slabs, they don't have any deeper meaning than just to merge all these wires because they serve the same function. Or am I wrong? I am wrong, because this is basically an AND whatever merge. So this has to be the preconditions. These must be the consume bits. So yeah, right. Just that I cannot understand the geometry. So like we have that as oh right. So this is actually, yeah, right. This is the AND gate. So this is all the wires which up to this point are relevant for this condition. And as we can see, with each block we go up, we get one more of these. That should be the same as this here. With each block we go, like with each carry we go up, C3, C4, we add one of these S's, the one of these consume factors. So that is actually what happens here. And with each direction we go in this, this direction, we have one less of these factors, obviously. And I just wonder where down here is the LSB. So the LSB is just relevant for these two. Okay, I'm not sure about that, because like if we have a look at this, the right, oh, there it is, the key point. Obviously the carry-in, or like the consume bit of the first half adder is of the first bit is only relevant for the carry-in. All the ones after that get generated later on, so they don't need to rely on the consume bit of the ones before. So that is why the low significant bit down here only serves the carry-in, which is this one, I guess. So here we got the carry-in and this wire. Oh, this lever is actually the carry-in, so okay, there we go. If we turn the carry-in on, this is the direct connection. That is like into like this one here, the direct, no wait, this one, that one, yeah, that one, the direct connection to the carry. That there's like no other condition. So oh, my computer is actually fast again for whatever reasons. So that is this wire here, this one. So, and if we want to have the carry-in enabled at the second position, we need to have the consume bit off. So this actually works quite fine. So with other words, looking at this and understanding this, or at least understanding that part of it, the conditions are the same, but the consume is like, okay, that makes sense. Okay, here comes my mind blow, whatever I just had. That is, if okay, I need to formulate this properly. If, right, it gets consumed when the output is 0. That is the only condition when it gets consumed. No, wait, it also gets consumed when it's AND. Okay, I failed this again. My mind blow just failed. That's like you speed up and run like, yeah, again, and then there's a wall, bam. Okay, it's awesome. I have this a bunch of times, and that's why so, because that is what we currently have. Like when there's an AND output here, it doesn't really matter for that one. But I think the carries are correct, right? The carry-in is only when the carry-in is on. What am I saying? So the point of, let's have a look. Yes, and that is because the AND still operates, so it needs to be off. But if I, for example, have an AND here going on, so let's ignore these wires for now. So let's say we have the first bit generates a carry, that is this line, that certainly arrives there, no problem. But if we now have a carry-in, that carry-in should cause this wire to be on, but it's not, for a reason I don't fully understand yet. Why is that? So what we have here is wait, this one should be on and that one should be off. Is that what I said? Yeah, I guess. So this one generates an carry and generates a normal output, and it should enable this one, but currently that one is blocking. Oh, obviously it's blocking it because it's consuming. This is off, so it consumes the well, it consumes the carry, but it doesn't receive the carry, as in this line is wait. Okay, this is the point where it gets ugly again. Probably gonna think hours about this. I need to understand this. It's important. Yes. That is not correct. Isn't it? Can I somehow color these bells? That is. Yellow. Red. Oh, let's not choose red. Let's go with orange. And that one, let it be yellow. And that one orange. And that one yellow. And I really get confused here. It's insane. Okay, some people, I think people who understand this anyway would watch it, and some people who don't understand it don't even know what I'm talking about. This is kind of annoying. But it's a good showcase of how this works. Let's see. 1 hour of me trying to understand something and failing. Okay, I'm really lost now. I think I go back to studying Minecraft. So there we go. There's like another condition for that one. That is kind of interesting. What is that? Is that? Oh, okay. See what I see? This one below here gets outputted as carry. It's like an extra condition I don't quite understand yet, and I should understand. Let me guess, it's the AND gate. Which would mean that this is well, it's using the OR because then it quicker arrives in the carry logic, but the AND is still there to well. So this is really an optimization which grants 1 tick of the whole adder. So that is actually maniac. Can I somehow somewhere have a look at this without going crazy? Yeah, exactly. So never mind the water, I am just derping. Wait, there's some VE command. Was it drain or something? Radius 60. Cool. You can totally rely on Volt on it. It's epic. So we need to know what this torch here is about and how this works. And okay, so this down here is the AND gate, if I got that right. So that means that these 2 blocks basically are our OR's output because we got this AND here. However, this is an Xor Gate, so this is an Xor actually. Huh. Interesting. So as you can see, if you can see, there's like a block going directly into this one and that block, and that one powers that torch, and that one gets powered by the other input for reasons like that one. So it's just a bunch of inputs going into there, I guess. Shouldn't like, oh man, this is crazy. Okay, that's the two inputs, and this is the propagate, and shouldn't there be something like this here? I don't know, maybe I destroyed that, doesn't matter. So we got the let's name this OR output for now, and then we got like that wire there and wire here and there. So yeah, this is an XOR output. So the question is, what gets pumped here? Is this actually the AND? This is the AND output of, yeah, as one can see here, this is like the AND, and this is the normal output, like the AND, which goes, the AND output, the generated carry of the first half adder. So the output which goes to the gates at the end is XOR. So that is the point which I missed here. So, and this is actually inverted, like here's the rest of the XOR, there's the inversion. So if this AND is on, then it won't work, and if the OR is on, then it also won't work. So so I'm saying, so if the input is 1 and 1, this goes off, so this goes on, and if this goes on, then we have no output because there's no XOR then working. However, if both of these are off, because 0 0, then this torch is on, which means if 0, so this one's off. So only if a combination of 1 that goes off and the other side. So it's a perfect XOR gate. Yay! What do we learn by that? We can use OR for the, let's call it propagate, but for the output we cannot. So this output we need to use XOR, else the whole thing won't work. Fact. OMG, that was kind of horrible. So what I can do at this point is I should disable this, like so, to get the proper result. This is just carry in and nothing. So if I go here and turn this on, this, it obviously works. I, however, want the carry to travel. Am I sane right now? 1 plus 1 is 2. Seems legit. Okay, in this case the carry travels like that. No, this is, it just gets generated there. Something like this. So these two are on. That means it's not getting consumed. It just travels through. But each of them receives a carry in. So this one gets the carry in. So this XOR is on and the carry is on. So this unit would in the past generate a carry that has been outsourced to here. Same for that one, that has been outsourced to here, and this wire is on, and these two don't really care if they're cancelled or not, because that's what this one checks for, like this checks it. So we cannot simply remove the XOR at this point. So how do we handle this part? And yeah, the answer is actually annoyingly truth. Whatever. It is required to do something like this. And then get rid of that one. Oh, should press T, then it works. So the point of this is that it will create the Xor again. So if I turn this in the OR mode, and I should maybe enable it again, then I need to ensure that result is like, wait, let me turn this off, everything. So if I turn on both here, we can see that this one is on, but it must be on because this one has to be disabled. So we basically can create another. Okay, I'm gonna do it like this. So at this point we got we need the XOR by having an OR. So this is our OR output, and which one do we need right now, the inverted or the non-inverted? We want this to be an AND gate, so we want to use the inverted one, which is that one. We want it to be on, but we don't want it to be on if the carry is on, and the carry is currently on. So if the carry is on, this has to be off, like so. So this is the perfect XOR representation, if I am right. As you can see, it's currently on. You have to look at that little piece of wire there. On, off, on, off. Yeah, that works. So everything which has been done now is that we disabled XOR in this unit to quicker reach the CLA or CLE logic, the triangle, the lookup, and then generate the XOR here again by just looking at the OR and the AND output of the first what is it, half adder. So it's just like we drag a component from here over to here to get that thing working. And if we do that, let me have a try. Let me test this. We do the same with the next unit. We're gonna grab that one and this one. The result should be correct. Everything is off. Works. So one. Oh, let me just flick through them. One works. So like this, and that does that. Then we got this one, that works perfect, that works perfect, that works perfect, that works perfect. So I claim this to be working. So with 3 bits, no, with 2 bits actually, and the carry out, I think I understood how, no, I don't think I understood how CLE works. Oh, but didn't I ask why the OR was also working instead of the XOR? We just know that it does because in Minecraft that's the case. Like, they use OR and it's equivalent. Obviously it's not for the output. That one needs the XOR, so we outsource the XOR, but for reasons the consuming is working too. And I don't quite understand why that is the case yet, which is, well, yeah. Why is it? Why does it have the same effect as before? We don't need the normal output. We need the inverted output of OR, and Okay, so let's have a look. So why is the inverted OR equivalent? If the OR is on, like if the OR is on, it's certainly not 0. In terms of, we have two cases. First is the half adder generates an AND, the other one, the half adder doesn't have input. That's the two cases when the carry gets consumed. So why is one of the cases, that is if the half adder generates a carry, irrelevant? I now get it. That is okay. Now I think I finally understood it. So the first most important relevant case is if right, okay, I got it. I got the image in my mind. Here it is, and no more this time. If we don't use XOR, that means we only consider the cases where there is no generated carry, only the cases where there is no input. Means if I generate a carry, then it's not consuming. Means it's not bypassing or not forwarding the carry, and it doesn't have to. The reason is simple, because whenever it generates a carry, like if the second one generates a carry, or let's take the first one because that one is done, then all the carries before are not relevant anymore, because then this one feeds the carry line already. So it doesn't have to bypass the carry, because the carry is set anyway. It's just set, so it doesn't really matter if it's how should I say, if it's on or off. It's really not relevant, and it consumes also. It consumes anyway, because the carry gets inserted before getting cut off into that unit. So the output is correct, and the forwarding is also correct, because the carry gets generated anyway. And if you have a little bit of clue of how this works, either you consume or you generate and consume. And if you do these two cases, it doesn't really matter, because the worst case what could happen is that you have a carry in and you generate a carry, and both carries collide on the carry transfer. But that will never happen, because whenever there's a carry generated, there will always be a carry consumed. So this collusion is just ignored, because it will 1 and 1 is 1, in OR, and that is what is it's OR, the carry. If you know, in the RCA you normally have a symbolic OR gate, which is commonly not drawn, because OR gates in these kind of simulation games are just, we connect wires. But that is an OR, and OR don't care how many ones come there. It's just one output. So we get a carry anyway. If there's a carry in or not, who cares? We generate a carry. So that is how it works. So my step from now is to, how should I say it? I know how it works now. I fully understand it. I need to put it in text form, so that my document is actually useful for other people, and so that they don't need to watch this washwater video of 1 hour and 10 minutes, but instead can just read in that same time the document and fully understand everything, instead of understanding nothing and looking at me how I struggle. Okay, if you really watched it, or if you watched parts of it, or whatever, or at least heard this ending, leave a comment, because why not? I don't care how you judge this video, but it's just me thinking literally. It has no big purpose, but that's how I understood this stuff. So whatever. Don't watch this video, just read the document. That's the main point. Okay, video and stop. Bye.